Morning, students. Am I audible? Seven. So we will wait for another 1 or 2 minutes. Only seven participants. We will wait for another 1 or 2 minutes. So we move on to the next part of the numerical. Okay. The first one is the rectangular channel. Second one is triangular channel. Okay. The triangular channel only the side slope is given. Okay. See, now what we are going to do, we are going to derive that YC expression for triangular channel. Okay, I think I have not given you the derivation. I have only give you the expression for YC for triangular channel. Okay, so what we are going to do, we are going to derive the expression, and in the examination you can directly use that expression for YC of a triangular channel. It is not to derive. Okay, and if you forgot, then you can also derive and then use. It's up to you. But the derivation is not required for your examination purpose. As I have not given you the derivation, so I am giving you. So this is your triangular channel. This is your depth of flow. We have considered YC because they ask us to find out YC. So the depth of flow we have considered YC, and your side slope is 1 is to Z. The Z value is 0.5. One vertical is to Z horizontal. Z is 0. This is your ZY and this is your ZY. So for your top width will be your twice ZY. Top width is twice ZY. This is your top width. Twice Z1. So you can say YC. And area is half into base into altitude. Okay? So see the area, okay, half multiplied by base. Base will be again twice ZYC, and then altitude is again YC. Okay? So this two will be cancelled out. Will be left out is ZYC square. This is the area expression of a triangular channel. Here, ZYC square. So you can see here the Z value is 0.5. Z value is 0.5. We can substitute here 0.5 YC square. Here in for the top width, if you substitute Z equal to zero point 0.5, 2 into zero point 0.5 to YC. It will be 1. 2 into zero point 0.5 is 1. Okay, to YC. That means the top width for our condition is YC and area is zero point 0.5 YC square. Okay. Now we are going to consider that critical flow condition, that Q square T divided by GE cube is equal to 1. Okay. And we replace the top width and the area. Okay. So you can see here, I think as we are going to derive that expression, we are not going to substitute the Z value. Okay? We keep that Z value as it is, because in our case it's zero point 0.5. For other case it may be different. Yes, that zero point 0.5 is not a constant part. As we are going for derivation, so we are going to keep the Z value as Z. Okay? Z is nothing but your side slope. So here Q square for the top width we have substitute twice ZYC divided by G is already there, or A cube we have substitute this Z cube YC to the power 6, because here it is square and then to the power cube is 6 equal to 1. You can see here we have numerator we have YC and denominator we have YC to the power 6. Okay. Here numerator we have Z, here Z cube. Okay. So this will be cancelled out and YC is also be cancelled out. So what is going to left out is Q square multiplied by 2 divided by G will be there, and Z cube is there, here is Z, so one Z will be cancelled out, so it will be get Z square. So here YC is there, then the numerator we have YC to the power 6, so Y on YC will be cancelled out, so it will be YC to the power 5 is equal to 1. As we are going to find an expression for YC, so we keep YC in one hand side. Okay. So if you put YC here, cross multiply, and this term will be left. Y is Q square G Z square. Okay. So this is the expression. Or you can say Y is Q square by G Z square to the power 1 by 5. This is the expression for critical depth of a triangular channel. Okay. So you write down P here. Okay. So this is the derivation. Okay. So during examination, directly use, if you remember the expression, you can directly use that expression and find out the YC value. Okay. The Z value is given zero point 0.5. Did not to find out the area and top width. Okay. Directly substitute that value here. Research is given, I think, 8.5, C is 9.81, and Z is zero point 0.5. You substitute here, find out the YC. First, you draw the diagram, because when you go for a derivation, the diagram should be there. Okay? First, you draw the diagram, then you find out the area expression and copy the expression. Okay? This part is not required. Okay? This part is not required. This part is not required. Only you find out the expression for area, conflict, and substitute in the critical flow condition. Okay? Over. So then you find out the YC value using this expression. You'll get around 2.26 meter. We find out the YC value and we will get approximately 2.26. So next, we need to find out the EC value for that particular critical condition for that triangular channel. For that, you can use this derivation or you can directly use this equation also. Is equal to 5 by 4 YC. Okay. This is nothing but you have to take that specific energy equation E square by will be YC plus V square by twice Z. Then V again you replace by Q by A. So this is a very simple derivation you can do. Okay. So at home you can try to derive this. Okay. Now you can directly take this. I think I have already given you this expression. Is equal to 5 by 4 YC. This is valid for only triangular channel. Then you find out the specific energy. EC you are going to get is 2.825 meter of water. So here we have completed that our third unit. Okay? That is specific energy chapter we have completed here. Okay? We move on to our new unit that is our gradually varied flow. Okay? So next you write gradually varied flow ZVF. I think ZVF, what is ZVF? We have already discussed. It's a non-uniform flow where that flow is gradually varying. Okay? First topic you write dynamic equation of GBF. GBF is gradually varied flow. Dynamic equation of gradually varied flow. Dynamic equation of gradually varied. For draw this diagram, we have already drawn this. Just roughly you can draw this diagram. Okay, that this is the bed of the channel. We have constructed an obstruction to flow of water. Then the upstream of that obstruction, we can see the water is gradually increasing, and after some time, it is overflow. That upstream or in the upstream section of this hydraulic structure, you can see that water is gradually increasing. This is our GBF. Okay? This is our mixing module. Gradually vary. You can draw this diagram, and then you will go for assumption. Okay? Here we are going to derive an expression for dynamic equation of gradually variable. For that derivation, we have taken some assumption to derive that particular derivation. So those assumptions we are going to discuss. First you draw this diagram, then you write dynamic equation of GBF, then you write assumption. You write first assumption, slope of the channel bed assumed to be very small. Write down the first assumption. Slope of the channel bed assumed to be very small so that depth of flow, that is y, is same in all sections. So first assumption. And second assumption is the channel is prismatic. Okay? Channel is prismatic, that is the cross section and slope is same throughout the channel. That is cross section and slope is same throughout the channel. Then you write number three, velocity coefficient alpha is assumed to be 1. Like unity, that is your alpha is equal to 1. We are going to consider that velocity coefficient is 1. Third is velocity coefficient alpha is assumed to be 1. Then number four is k and z are exponential function of depth y. K and z are exponential function of depth y. K and z you have already know, we have already discussed many times. Z is section factor that we have already discussed. The So number four, you write k and z are exponential functions of depth y. Next, you write for five you write roughness coefficient small n or c or f. Okay. One is your Sages constant, one is your Manning's roughness coefficient, and friction factor f is independent of depth of flow and constant throughout the channel. Roughness coefficient, that means whatever the n value we are going to consider, that we are assume that it will be constant throughout the channel. Similarly, if we consider Sages constant or friction factor, though we all know these terms are not constant, it's varying when it moves from one place to another. Okay? But we are to simplify our calculation or simplify our derivation, we are going to consider this term as constant throughout the channel. The number five assumption is roughness coefficient n or c or f is independent of depth of flow and constant throughout the channel. Then move on to the last assumption. A head loss at a certain section, a head loss at a certain section is same as for an uniform flow. Head loss at a certain section same as for an uniform flow. That is, uniform flow formula such as Manning's equation, Sages equations are applicable in gradually varied flow to find out the friction or energy stream. What they are saying that head loss for a certain section is same or it's similar to your uniform flow. That is, or Manning's and Sages equation, which are applicable for uniform flow, can also be used in gradually varied flow to find out the energy or friction stream. So you write down the last assumption. A head loss at a certain section is same as for an uniform flow. That is, uniform flow formula such as Manning's and Sages equation are applicable in gradually varied flow to find out the energy and friction stream. over. Then we go for the derivation. So before the derivation, kindly draw this diagram. Okay, figure you write derivation of the derivation is cannot be completed in a class. So we are going to derive in the next class. Okay, because half of the class is already over. So, but you draw this diagram now. Okay, otherwise again in the next class we will be having the same. So if you complete in one class, then it's better for us. So you kindly draw this diagram. Draw this diagram. Good. So we are going to end this class here. Okay? Again in the next class, we are going to derive a dynamic equation of Brazilian